Hello dear friends and welcome to this video. As promised, today we will explore a very interesting and exciting topic. I would be grateful if you would like my efforts, and we will begin now. Are you ready? What does it mean when a comet seems to release water in deep space? Far beyond the warmth of the sun, where most objects remain frozen and inactive, a traveler called 3I Atlas is producing about 40 kilograms of water every second. At that distance, such behavior should not be possible. Astronomers describe it as unusually active, almost behaving like something alive, though it is entirely made of rock, ice, and dust. 3I Atlas is not an ordinary comet. It is an interstellar object, meaning it did not form in our solar system. It arrived from another star's environment, bringing a chemical composition and behavior that differ from what we normally observe. Its emissions contain nickel without iron, traces of cyanide, and other compounds that do not fit the typical ratios found in comets that orbit our Sun. The first clear signs of activity came from the Swift Space Telescope in early 2025. Swift was originally designed to detect gamma-ray bursts, but its ultraviolet instruments also allow it to study comets. When it observed 3I Atlas, it detected a large cloud of hydroxyl molecules surrounding the comet. Hydroxyl, or OH, appears when sunlight splits water molecules apart. Its presence means that the comet was releasing water in large quantities. The numbers are remarkable. At a distance of roughly 3.5 astronomical units from the Sun, more than 3 times farther out than Earth 3I Atlas was producing about 1.3 times 10 to the 27th water molecules per second. That equals around 40 kilograms of water every second, or roughly the mass of a small car evaporating into space every minute. For comparison, most comets in our solar system remain inactive at that distance. They stay frozen until they approach much closer to the Sun, where sunlight is strong enough to cause water ice to sublimate, that is, to turn directly from solid to gas. The sunlight at 3.5 astronomical units is far too weak to drive that process. Yet this comet is doing exactly that. Other interstellar visitors have behaved differently. The first known one, Oumuamua, passed through in 2017. It showed no visible gas or dust, just a silent tumbling object that reflected sunlight but produced no outgassing. The second Borisov, discovered in 2019, was more typical. It emitted gas and dust in the way ordinary comets do. 3I Atlas, however, does not follow either example. It is far more active, releasing material where our comets would remain dormant. This raises important questions about what is causing such behavior. Scientists are exploring several possibilities. One idea is that the comet contains unusual types of ice, perhaps compounds that sublimate at lower temperatures than ordinary water ice. Another theory suggests internal heating. The comet might still retain warmth from its original formation billions of years ago. Some researchers also consider mechanical explanations, such as rotation patterns, that concentrate sunlight on specific regions of the surface. Chemical reactions inside the nucleus could also contribute, though none of these mechanisms fully explain what is observed. The comet's spectrum reveals not just water vapor, but also carbon dioxide, cyanide, and atomic nickel in unexpected amounts. Each compound offers clues to the temperature and chemistry of its environment of origin. In this case, the ratios between them do not match anything known in our solar system. That difference suggests the comet was built from materials exposed to different radiation levels, temperatures, and pressures, conditions unique to another star's protoplanetary disk. For astronomers, This makes 3i Atlas an important opportunity. Every telescope capable of observing it has turned to study the comet in as many wavelengths as possible: ultraviolet, visible, infrared, and radio. Instruments measure its light output, track its motion, and analyze how its brightness changes with distance from the Sun. By combining all these observations, scientists hope to understand not only the comet's behavior, but also the physics of the star system where it formed. 3i Atlas may be small, but it carries valuable information. Its activity challenges long-held assumptions about how comets behave in cold regions of space. It may reveal new processes that occur in materials under extreme conditions, processes that could exist elsewhere but have never been observed up close. For now, astronomers continue to collect data, comparing each new measurement with existing models. Every result adds a small piece to the puzzle. The comet's behavior is unusual, but not necessarily impossible. It is a reminder that our understanding of cosmic chemistry is still incomplete. 3i Atlas might not rewrite the laws of physics, but it is expanding the boundaries of what we thought those laws allowed. One of the most puzzling findings about 3i Atlas is the detection of nickel in the gas it releases, but without the usual presence of iron. Normally, these two elements appear together in nearly constant proportions. They are both produced in the same stellar processes and are chemically similar, so they tend to evaporate under similar conditions. In comets from our solar system, nickel and iron always appear side by side. However, observations made by the European Southern Observatory and NASA's spectrographs show that 3i Atlas emits a clear nickel signal while iron remains undetectable. This imbalance suggests that the material inside the comet was formed under very different physical and chemical conditions. In most environments, nickel and iron condense together when temperatures fall below about 1000 degrees Celsius. To separate them, you would need an environment with specific temperature and pressure conditions that are not common in our solar system. That is why the discovery is so interesting. It implies that 3i Atlas might have originated in a region of its parent star system where chemical separation was possible, perhaps close to the star, where nickel compounds could survive while iron condensed out differently, or far in the outer disk, where the chemistry followed a completely different pattern. Either scenario challenges what we know about the early stages of planetary formation. The comet also shows unexpected patterns in the amount of carbon-bearing molecules. For instance, the levels of carbon monoxide and carbon dioxide differ from those measured in typical long-period comets. This suggests that the ratio between carbon and oxygen in its birthplace could have been different from the solar value. Such variations influence the types of solids that form in a disk and the eventual makeup of planets and smaller bodies. Spectral studies have also found signs of hydrogen cyanide, a compound containing hydrogen, carbon, and nitrogen. It is common in comets, but the concentration here is unusually high. Hydrogen cyanide plays an important role in prebiotic chemistry, meaning it can form more complex organic molecules under the right conditions. The presence of such a compound in large quantities provides information about how organic chemistry begins in other planetary systems. Another point of interest is the comet's dust. Instruments analyzing the scattered light have revealed a particle size distribution that differs from most comets observed before. The dust grains appear smaller and more reflective, which might explain why the comet appears brighter than expected. Differences in grain size can affect how a comet interacts with sunlight and how quickly it heats up or cools down. All of these properties together, unusual nickel emission, high cyanide content, and active water release at long distance, point toward an origin in a region with very specific conditions. Researchers suspect that the comet might have formed in the cooler outskirts of its original protoplanetary disk, then was ejected into interstellar space by gravitational interactions with larger planets. Over time, it traveled through space for millions or even billions of years before entering our solar system. Even after such a long journey, it has retained enough volatile material to remain active. That means the surface and interior of the comet must be well insulated, preventing its ice from fully evaporating in interstellar space. Studying how that insulation works could help scientists understand the structure of cometary nuclei more generally. To explore this, astronomers are using a combination of ground-based telescopes and space observatories. Instruments like the Very Large Telescope, the Hubble Space Telescope, and the James Webb Space Telescope all contribute to the ongoing analysis. Each observes the comet at different wavelengths, building a complete picture of its composition. Ultraviolet data reveal the breakdown of water and other volatile molecules. Infrared measurements detect organic compounds and ices that are invisible in other ranges. Radio observations track the outflow of gas and dust in 3 dimensions, helping to model the rotation of the nucleus and the direction of its jets. By combining these data sets, scientists can simulate how sunlight and internal energy sources interact to produce the observed emissions. The modeling process is complex but essential. It helps determine whether the comet's activity can be explained by normal sublimation processes or if entirely new mechanisms are involved. So far, the data suggests that some traditional explanations still apply, but only partially. There might be an additional source of energy or a material property that we have not yet accounted for. Another possibility under discussion is that the comet's surface has areas rich in highly volatile compounds such as carbon monoxide or methane. These substances can evaporate even at very low temperatures, creating localized jets of gas that drive the observed activity. If this is correct, 3I Atlas could represent a transitional object between a typical comet and an icy body from the outer regions of another solar system. Whatever the exact cause, the object is now considered one of the most scientifically valuable interstellar visitors ever detected. Unlike Oumuamua, which passed by silently, or Borisov, which followed predictable patterns, 3I Atlas offers a chance to study an active, dynamic body from another star. It shows that the processes of planetary formation elsewhere are not identical to those we see at home. As data continue to accumulate, teams around the world are working on refining the models that describe how such bodies evolve. Each new observation reduces uncertainty and helps connect the dots between our solar system and others. If these results hold, 3I Atlas might become a reference point, a standard for comparing interstellar comets and understanding how different cosmic environments shape them. For the public, the story may seem abstract, but for scientists, this comet is a natural experiment that cannot be repeated. Every detail matters: the rate of gas emission, the balance of elements, even the shape of its light curve. Each clue brings us closer to understanding how matter behaves under unfamiliar conditions, and how systems beyond our sun might differ from what we know. As more observations accumulate, researchers are building a detailed timeline of how 3I Atlas behaves while moving through the solar system. Tracking this behavior helps determine whether its level of activity changes in response to sunlight or if other internal processes dominate. The data show that the comet's outgassing rate does not follow the usual solar heating pattern. Most comets become more active in a predictable way as they approach the Sun, with a steady increase in gas and dust emission. 3I Atlas, however, shows irregular fluctuations. At some distances, it produces large amounts of gas, while at others, its output drops unexpectedly. This inconsistency points to internal factors such as uneven distribution of volatiles, local fractures on the surface, or thermal lag, the delay between heating and sublimation. To analyze these variations, astronomers are applying thermal models originally developed for the Rosetta mission, which studied Comet 67P, Churyumov, Gerasimenko. These models simulate how sunlight penetrates surface layers, how heat travels through porous material, and how different ices respond to small temperature changes. When these models are adjusted for 3I Atlas, the predicted behavior still does not fully match what is observed, meaning that its internal structure must differ significantly from typical comets. Another focus of study is the rotation of the comet. Changes in brightness and jet direction suggest that the object is spinning, but the rotation period remains uncertain. Some datasets indicate a rotation period of several hours, while others imply longer cycles. If the nucleus rotates unevenly, sunlight may periodically reach different active zones, causing bursts of activity followed by quiet phases. This could explain some of the irregular patterns in gas production. Dust analysis has also advanced. Spectropolarimetric observations, which measure how light becomes polarized when reflected by dust particles, reveal that the composition and texture of the grains differ from those of local comets. The degree of polarization implies that the particles are less compact and contain more transparent minerals. This affects how light scatters and may be one reason the comet appears unusually bright at certain angles. By mid-2025, several observatories have coordinated campaigns to monitor the comet simultaneously. The goal is to create a continuous light curve, a record of its brightness over time, combined with high-resolution spectra. Such coordinated observations allow scientists to link changes in brightness with specific chemical emissions. When a spike in water vapor coincides with a rise in brightness, it often means a fresh layer of ice has been exposed to sunlight. Interestingly, 3I Atlas shows strong activity even as it moves away from the Sun. This persistence suggests that either its volatile materials are unusually abundant or its internal layers retain heat efficiently. Both possibilities point to a different internal composition from standard comets. Chemical modeling supports this idea. When researchers input the observed gas ratios into standard solar system-based models, the results fail to reproduce the measured spectra. To match the data, the models require adjustments in key parameters such as the ratio of carbon to oxygen and the relative abundance of refractory metals. These adjustments point to a formation environment with lower metallicity and perhaps a weaker stellar wind than our Sun produces. Such an environment could influence how dust grains and ice condense in the protoplanetary disk. If the parent star emitted less ultraviolet radiation, organic compounds might have survived closer to the star, creating a different distribution of materials. The composition of 3I Atlas could therefore represent a snapshot of such an alternative disk, preserved and carried across interstellar space. The study of interstellar comets like this one has broader implications. It allows astronomers to test theories about how common certain types of planetary systems are in the galaxy. If the composition of 3I Atlas proves to be rare, it might mean that our solar system's chemistry is not typical. But if future interstellar objects show similar patterns, it could indicate that many systems share a comparable chemical evolution. Instrument calibration also plays an important role in these studies, because the signals from interstellar comets are faint and distant. Small errors in data processing can lead to misleading conclusions. Research teams spend months cross-checking spectra from different instruments to ensure consistency. Only after confirming the same chemical signatures across multiple telescopes do they publish final results. A growing database now stores all available measurements of 3I Atlas, gas production rates, dust properties, orbital data, and light curves. This centralized archive allows international collaboration and comparison with other known comets. As new instruments come online, such as the Vera-Rubin Observatory, the data will help identify similar interstellar objects in the future. Beyond pure research, missions are being discussed to study interstellar visitors more directly. Agencies like NASA and ESA are evaluating designs for spacecraft capable of intercepting or flying by future comets entering the solar system. These missions would provide direct sampling of material formed around other stars. Although no such mission can reach 3I Atlas itself due to its trajectory, its discovery strengthens the case for developing such technology. From a scientific perspective, every interstellar comet provides a unique opportunity to expand our understanding of cosmic diversity. 3I Atlas, in particular, bridges multiple disciplines, planetary science, astrophysics, and chemistry, by combining data from across the electromagnetic spectrum. Its study continues to refine our models of how matter evolves from interstellar gas to solid bodies, and eventually to planetary systems. Even though much remains unexplained, the overall picture becomes clearer. 3I Atlas is active because of conditions and materials uncommon in our solar neighborhood. Its persistence at low temperatures suggests internal heat storage or the presence of exotic ices. Its chemical fingerprint differs enough to indicate a separate cosmic origin, yet similar enough to confirm shared physical laws. Every observation of this comet adds one more reference point to the larger effort of mapping how stars and planets form throughout the galaxy. The more we learn from such objects, the closer we come to answering fundamental questions about how common or rare our own planetary system truly is. As attention around 3I Atlas continues to grow, scientists are rethinking how often interstellar objects might enter our solar system. For decades, such visitors were considered extremely rare. Before 2017, not a single one had been identified with certainty. The detection of Oumuamua and then Borisov changed that perception, and the discovery of 3I Atlas further supports the idea that interstellar objects could be more common than previously believed. Statistical analysis suggests that thousands of such bodies may cross the solar system each year, though most go unnoticed because they are small, faint, or pass too far from Earth to be detected. With the next generation of observatories, including the Vera-Rubin Observatory, the ability to find them will improve dramatically. When operational, its wide-field survey will scan the sky repeatedly, capturing fast-moving, dim objects that older telescopes might miss. Knowing how frequently these objects appear is essential for designing missions capable of intercepting them. Unlike comets native to our solar system, interstellar visitors often travel at high relative speeds and along unpredictable trajectories. Planning a spacecraft launch requires early detection, ideally months or even years in advance, to calculate a feasible intercept path. The upcoming Comet Interceptor mission by the European Space Agency is designed with this flexibility in mind. It will wait in a holding orbit, ready to be redirected once a suitable target is discovered. 3I Atlas cannot be reached by any current or planned spacecraft, but its observation has directly influenced mission design. Engineers now consider instruments capable of rapid response, high-resolution imaging, and flexible data transmission. These capabilities are critical for capturing short-lived events such as volatile outbursts or sudden fragmentation. In the case of interstellar comets, every minute of data counts because their visit is brief and cannot be repeated. The chemical diversity observed in 3I Atlas also contributes to ongoing discussions about the origin of organic compounds in space. Molecules such as hydrogen cyanide, carbon dioxide, and water are not rare, but their ratios vary significantly between comets. Comparing these ratios helps determine whether organic chemistry develops similarly in different star systems or depends on unique local conditions. If multiple interstellar comets display similar molecular patterns, it would imply that organic chemistry across the galaxy follows universal rules. This topic connects directly to astrobiology. While no one expects life to originate inside a comet, the ingredients for life can. Comets deliver water, carbon, and nitrogen, all necessary for complex molecules, to young planets. Studying interstellar comets therefore reveals what types of chemical ingredients may be available in other planetary systems. If 3I Atlas formed around a relatively cool star, for instance, it might contain organic compounds that survived radiation that would destroy them near hotter stars. To analyze such material remotely, astronomers rely on spectroscopy. Each molecule absorbs and emits light at specific wavelengths, leaving unique patterns in the observed spectrum. High-precision instruments like those on the James Webb Space Telescope can detect these patterns even at great distances. Webb's infrared capabilities make it particularly effective at identifying carbon-based molecules and ices that remain invisible in visible light. Data from Webb have already confirmed the presence of several organic compounds in the gas surrounding 3I Atlas. In parallel, laboratory scientists simulate cometary conditions on Earth. They create ice mixtures that match the observed compositions and expose them to vacuum chambers at temperatures similar to those in space. These experiments test how different compounds behave when irradiated by light or cosmic rays. By comparing laboratory spectra with actual telescope data, researchers refine their understanding of the comet's chemistry. The results from such simulations are valuable for planetary science as a whole. They inform models of how material evolves in protoplanetary disks, how volatiles migrate during planet formation, and how organic molecules survive in extreme environments. Insights gained from one interstellar comet can apply to the study of disks around distant stars observed by facilities such as ALMA, the Atacama Large Millimeter, Submillimeter Array. Another area of active research involves the dynamics of ejection, how objects like 3I Atlas leave their parent systems. Gravitational interactions between forming giant planets and smaller icy bodies can send some of them outward at high velocities. Once they escape their star's gravity, they drift through interstellar space indefinitely until captured temporarily by another star's gravity. Understanding these dynamics helps estimate how much solid material travels between star systems over cosmic time. Simulations suggest that each planetary system could eject billions of small bodies during its formation phase. This means interstellar comets might be abundant in the galaxy, even if only a few pass close enough to be seen. The discovery of 3I Atlas therefore fits into a broader picture in which planetary formation naturally produces a continuous exchange of material between stars. For humanity, studying these travelers is also a technological challenge. The ability to track, analyze, and eventually visit interstellar objects demonstrates the level of precision space agencies have achieved. Each new discovery pushes observational techniques further, requiring faster data processing, more sensitive detectors, and better coordination between ground and space observatories. From a communication perspective, it also changes how the public perceives the universe. When people hear that a piece of another star system has entered our own, it transforms abstract astrophysics into something tangible. It shows that the solar system is not isolated. It is part of a larger network of matter moving through the galaxy. In the coming years, continued monitoring of 3I Atlas will provide data even after it leaves the inner solar system. Long-range observations can track how its activity fades and whether any structural changes occur as it cools again. These details will complete the picture of how interstellar comets behave during their passage. By combining all this information, composition, dynamics, and evolution, scientists can begin to answer broader questions. How diverse are the building blocks of planetary systems across the galaxy? Are our solar system's materials typical or unusual? And what can these visiting objects tell us about the environments in which other worlds are born? 3I Atlas is one data point among many that will eventually define a statistical view of planetary formation beyond our Sun. Each measurement brings us closer to a complete understanding of how matter circulates in the galaxy and how often those materials come within reach of observation. The discovery of 3I Atlas has deepened the discussion about the origin of matter in the galaxy. Every element and molecule in the comet must have formed under specific conditions, in a disk of gas and dust surrounding a young star. By studying this object, scientists can infer what those conditions were and how they differ from the environment in which our own solar system formed. When a star is born, its surrounding material contains a mix of hydrogen, helium, and heavier elements created by earlier generations of stars. The relative proportions of these elements determine the chemistry of any planets and comets that form there. In our solar system, the ratios of carbon, oxygen, silicon, and metals are well understood. But the composition of 3I Atlas shows clear differences, suggesting it came from a region where those ratios were not the same. In particular, the comet's lack of detectable iron, along with the presence of nickel and volatile carbon compounds, indicates a formation environment with lower metallicity. In astrophysics, metallicity refers to the abundance of elements heavier than hydrogen and helium. Stars with lower metallicity tend to form earlier in galactic history, which means 3I Atlas may have originated around an older, cooler star. If this is the case, the comet's materials could represent an earlier stage of galactic chemical evolution, a sample of conditions that existed billions of years before our solar system formed. That makes it a valuable record of how matter changes over time. Comparing its composition with younger comets helps scientists understand how the galaxy gradually accumulates heavy elements and organic molecules. Organic chemistry plays an important role here. Simple molecules like hydrogen cyanide, methane, and formaldehyde can form under many different conditions, but their abundance and stability depend on temperature, radiation, and the presence of dust grains. The relative balance of these factors determines whether complex organics can survive long enough to be incorporated into planets. In 3I Atlas, high levels of hydrogen cyanide suggest that organic synthesis was efficient in its original disk. Laboratory experiments show that when ices containing these molecules are exposed to ultraviolet light, they can form amino acids and other prebiotic compounds. This process happens without requiring biological activity, just chemistry and radiation over long timescales. Detecting such compounds in an interstellar comet means that similar processes likely occur throughout the galaxy. Spectroscopic data from the James Webb Space Telescope confirm that the comet's infrared spectrum includes absorption features consistent with complex hydrocarbons. Although these molecules are not evidence of life, they show that the building blocks for life exist in diverse environments. If comets like this one are common, it suggests that the ingredients for organic chemistry are widespread, and the early stages of planet formation almost always involve organic material. Researchers are cautious when interpreting these findings. Some compounds can form or change as the comet interacts with sunlight in our solar system. Distinguishing between what was originally present and what formed recently requires detailed modelling. Scientists compare 3I Atlas's current emission spectrum with theoretical spectra based on different radiation intensities to estimate how much its composition might have changed since entering the solar system. So far, results indicate that the major features, the water, cyanide, and nickel signatures, are intrinsic, not products of solar heating. This strengthens the idea that the comet's chemistry reflects its original formation environment. From a cosmochemical perspective, this discovery supports the concept of galactic mixing. Over billions of years, material ejected from dying stars spreads through the interstellar medium and becomes part of new systems. Interstellar comets act as carriers of that recycled material. Each one brings a sample of matter that once belonged to a different star, now crossing our own region of space. Studying them gives direct insight into how elements and molecules move between generations of stars. The next step for scientists is to determine how often such mixing occurs and how diverse the compositions of interstellar comets are. If most of them share similar traits, the galaxy may be more chemically uniform than expected. If they differ widely, it means that local conditions around each star play a stronger role in shaping planetary systems. Data from future missions and surveys will be crucial for testing these ideas. Observatories capable of rapid spectroscopic measurements will help identify and compare new interstellar comets in real time. The more examples researchers collect, the better they can build a statistical model of how material circulates in the Milky Way. These studies also have implications for our understanding of early Earth. Many theories propose that comets delivered a significant portion of Earth's water and organic matter. By observing comets from other star systems, scientists can assess whether such deliveries could happen elsewhere. If interstellar comets frequently pass through young systems, they might contribute material that influences the chemistry of developing planets. For now, 3I Atlas serves as both a data source and a test case. It provides evidence that the chemical pathways leading to complex molecules operate under a wide range of conditions. Its continued observation will refine our understanding of how interstellar material contributes to the evolution of galaxies and the formation of habitable environments. In summary, this comet is more than just a visiting object. It is a physical record of another star system's history. Its unusual chemistry, stable activity, and rich organic content make it one of the most informative interstellar discoveries to date. Ongoing analysis and future comparisons with similar objects will help answer how universal the processes of chemistry and planet formation truly are. To understand how interstellar comets like 3I Atlas reach our solar system, scientists use dynamic simulations that trace their possible paths through the galaxy. These models take into account gravitational interactions with nearby stars, molecular clouds, and the general structure of the Milky Way. The goal is to estimate how objects are ejected from their home systems and how often they might cross ours. Ejection typically happens during the early stages of planetary formation. When large planets form, their gravity can scatter smaller bodies, sending some of them inward toward the star and others outward into space. If a smaller object gains enough energy from such encounters, it escapes the gravitational pull of its star completely. Once free, it travels through the galaxy along an independent trajectory. These objects can wander for millions or even billions of years before encountering another star. The Milky Way's disk contains countless such fragments, icy and rocky remnants of planetary systems. Some may eventually pass close enough to the Sun to be detected, as 3I Atlas did. When scientists run numerical simulations of these interactions, they find that ejections are common, especially in systems with massive gas giants. The gravitational slingshot effect produced by these planets can accelerate small bodies to escape velocity with relative ease. Because most stars have planetary systems, this means interstellar comets should be widespread throughout the galaxy. To estimate the frequency of encounters with our solar system, astronomers combine galactic models with data from recent detections. The results suggest that small interstellar objects, less than 100 meters across, may pass through the solar system every few months. Larger ones, like 3I Atlas, are rarer, perhaps a few per decade, but still far more frequent than once believed. Tracking these objects requires precise calculations of their orbits. When an interstellar comet enters the solar system, its trajectory follows a hyperbolic path rather than the elliptical orbit of local comets. This hyperbolic motion means it will pass once and never return. The exact shape of its path provides information about its velocity relative to the Sun and the direction from which it arrived. For 3I Atlas, the calculated hyperbolic excess velocity, the speed it has even after escaping the Sun's gravity, is around 25 kilometers per second. This is consistent with the expected range for objects moving within the general stellar population of the Milky Way. The direction of approach places its origin somewhere near the constellation Perseus, although pinpointing a specific parent star is nearly impossible. Over millions of years, small gravitational perturbations erase any clear link to its birthplace. Another key parameter is the inclination of the comet's trajectory relative to the plane of the solar system. 3I Atlas entered at a steep angle, which helps confirm its interstellar nature. Native comets tend to orbit close to the ecliptic plane, following the general distribution of solar system material. A high inclination indicates that the object was not shaped by the same processes. Dynamic modeling also explores what happens as such an object passes through the solar system. As it approaches the Sun, It interacts gravitationally with the planets, especially Jupiter, whose large mass can slightly alter its path. In most cases, the effect is minimal, but in rare situations, Jupiter's gravity could either slow an object enough to trap it temporarily or accelerate it further, changing its exit direction. Researchers run thousands of simulated trajectories to explore all possible outcomes. These simulations help predict how future interstellar comets might behave and how close they might come to Earth or other planets. Although the probability of collision is extremely low, the study of these paths helps refine models of orbital dynamics and the influence of planetary systems on passing bodies. Such modeling also provides insights into the stability of planetary systems. The fact that comets can be ejected so easily implies that many systems lose a significant fraction of their small bodies during formation. This process might even shape the distribution of debris disks observed around other stars. By comparing those observations with simulations, scientists can infer how common large-scale scattering events are in young systems. A related question is whether interstellar objects can ever be captured permanently. Theoretically, a precise gravitational interaction with planets could slow an incoming comet enough to bind it to the Sun. However, the likelihood of such an event is extremely small. So far, no confirmed case of a captured interstellar object exists, though statistical models suggest it could happen once every few million years. These findings help frame the broader understanding of how material moves through the galaxy. The exchange of small bodies between stars is not random. It follows the structure of the Milky Way's disk and spiral arms. Regions with higher stellar density, such as near the galactic center, may experience more frequent exchanges. The Sun, located in a relatively calm region of the galaxy, still encounters a steady flow of interstellar material over time. Observations of 3I Atlas contribute to refining these galactic models. By combining its measured velocity and trajectory with data from other objects, astronomers can map how debris travels between stars. These datasets are compared with simulations of the galaxy's gravitational potential to estimate how often such comets pass near stars like the Sun. The current models predict that thousands of interstellar comets similar in size to 3I Atlas exist within a few light years of the Sun at any given time. Most are too faint to detect, but future telescopes with larger apertures and improved sensitivity will be able to identify many more. With enough detections, researchers will be able to chart the density and distribution of interstellar debris across the local region of the Milky Way. Ultimately, understanding these dynamics is crucial for interpreting the role of interstellar material in shaping planetary systems. Each comet, like 3I Atlas, represents a connection between stars, a piece of another system that now temporarily belongs to ours. With each new interstellar comet detected, the statistical picture becomes more detailed. Astronomers now estimate that the Milky Way contains an enormous number of free-floating small bodies, perhaps more than there are stars. Most are remnants of planet formation processes that took place billions of years ago around other stars. These fragments serve as physical evidence that the creation and evolution of planetary systems are ongoing throughout the galaxy. 3I Atlas is part of this wider population. Its measured properties fit within the expected range for interstellar debris, confirming that such objects are not unique but part of a continuous distribution. The difference lies mainly in detection limits. Only the brightest or closest ones can be studied in detail. As observation technology improves, fainter and smaller objects will gradually enter our catalogue. To quantify the total population, researchers use mathematical models that link observed comets with predicted density distributions. These models assume that each planetary system ejects billions of small icy and rocky bodies during its formation phase. Over time, this material fills interstellar space with a nearly uniform background density. When the Sun moves through the galaxy, it passes through this diffuse population. Occasionally, some of these bodies enter the solar system's gravitational sphere and become visible as interstellar comets. Simulations indicate that the density of such material could reach about one object larger than 100 meters per cubic astronomical unit. Although that sounds low, it translates to billions of objects within a few light years of the Sun. Most are too small or too dark to detect, but their collective presence influences the overall dynamics of the galactic disk. This continuous exchange of matter between stars plays an important role in galactic evolution. When comets and small bodies travel from one system to another, they redistribute elements and molecules, mixing the chemical composition of different regions. Over billions of years, this process contributes to the chemical uniformity observed across much of the Milky Way. It also ensures that heavy elements and organic compounds created by one generation of stars become part of the raw material for the next. For scientists studying planet formation, these findings support the idea that no planetary system develops in isolation. Each is part of a broader network of material exchange. Some of the atoms that make up Earth may once have belonged to a different star system. Similarly, fragments from our solar system may one day drift into others, carrying traces of our own chemistry outward. The data collected from 3i Atlas also help refine the distribution of velocities among interstellar objects. The comet's motion is consistent with that of the local standard of rest, the average motion of stars in the Sun's neighborhood. This suggests that interstellar comets share the general kinematics of nearby stellar populations rather than moving in random directions. Understanding this distribution helps astronomers predict where to look for future detections. Improving detection methods is a key goal. Most current surveys are optimized for objects that move slowly across the sky. Interstellar bodies, however, appear to move quickly due to their high velocities. Specialized algorithms are now being developed to identify such fast-moving targets automatically. When combined with large-scale surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time, these tools are expected to increase detection rates significantly. In addition to optical surveys, infrared and radio instruments are becoming important. Some interstellar objects may not reflect much visible light, but emit weak infrared radiation as they absorb sunlight. Sensitive detectors operating in these wavelengths can reveal objects that optical telescopes might miss. Radio arrays can detect the interaction between solar radiation and outgassing materials, providing another way to identify comets passing through the outer solar system. Every detection adds to the dataset that defines the structure of interstellar debris. When enough observations are collected, scientists can create three-dimensional maps showing the distribution of such material across nearby space. These maps may reveal concentrations of debris near certain stellar groups or along galactic spiral arms. Such information will improve our understanding of how material circulates within the Milky Way and how often new stars inherit interstellar dust and ice from previous generations. From a theoretical standpoint, the exchange of matter through interstellar comets connects local planetary science with galactic astronomy. It shows that small-scale processes, like the ejection of a comet from a planetary disk, contribute to large-scale galactic evolution. By combining observational data with computer models, scientists can link the formation of individual planets to the broader behavior of the galaxy as a whole. Another area of active research focuses on the role of interstellar material in the early stages of star and planet formation. When clouds of gas and dust collapse to form new stars, they incorporate existing interstellar solids. These solids act as condensation nuclei around which ices and organics can gather. The presence of pre-existing complex molecules may accelerate chemical evolution in young disks, potentially influencing how quickly habitable conditions arise on forming planets. In this sense, interstellar comets like 3I Atlas are more than scientific curiosities. They are participants in a long-term galactic cycle that redistributes the ingredients of planets and atmospheres. By understanding their composition and trajectories, we gain insight into how material circulates between stars and how the galaxy maintains its chemical balance over time. Although the direct study of individual interstellar comets is challenging, their cumulative effect on galactic chemistry is significant. The information carried by each one, the ratios of elements, isotopic signatures, and molecular structures provides a record of past environments that no other method can access. By analysing even a few such objects in detail, astronomers can trace the evolution of matter across billions of years and vast distances. Progress in the study of interstellar comets depends strongly on new observational technology. The current generation of telescopes can identify only a small fraction of the objects that actually pass through the solar system. Upcoming facilities aim to change that by combining wide field coverage, high sensitivity, and automated data analysis capable of detecting fast-moving targets in near real time. The Vera Rubin Observatory will be central to this effort. Its legacy survey of space and time will scan the entire visible sky every few nights, generating an enormous catalogue of moving sources. Specialized software will analyze brightness variations and motion patterns to flag potential interstellar objects within hours of observation. This rapid identification will allow ground and space-based telescopes to start follow-up studies before an object travels out of range. At the same time, improvements in spectroscopy are making it possible to analyze smaller and fainter targets. Modern spectrographs can record thousands of wavelengths simultaneously, capturing the chemical fingerprints of multiple compounds in a single exposure. Portable versions installed on medium-sized telescopes will make routine chemical surveys feasible even for modest observatories. In space, infrared instruments continue to expand capabilities. The James Webb Space Telescope has already demonstrated how detailed infrared spectra can reveal complex organic molecules that remain hidden in visible light. Future infrared missions, such as the planned Origin Space Telescope, would extend this reach to colder and more distant comets, giving a clearer view of their internal composition and thermal behavior. Another technological development involves radar and radio observations. While these methods are less sensitive to light-reflecting properties, they can detect how a comet's plasma interacts with solar radiation. Radio telescopes measure the emission lines from molecules such as hydroxyl and hydrogen cyanide, allowing precise calculations of gas production rates. The data help refine models of outgassing and can confirm the interstellar nature of a target without direct imaging. Parallel to optical and radio improvements, computing power has become a decisive factor. modern data pipelines process terabytes of raw images daily. Machine learning algorithms trained on simulated interstellar trajectories can now classify moving objects by their orbital characteristics automatically. This automation reduces human error and ensures that no unusual object is missed because of observational bias. In mission design, agencies are exploring strategies for flexible spacecraft capable of intercepting short-notice targets. ESA's Comet Interceptor, scheduled for launch later this decade, is a major step toward that goal. The spacecraft will wait at the Sun-Earth Lagrange point L2 until a suitable target is found. Once identified, it will be redirected to perform a close flyby, taking high-resolution images and in-situ measurements. While designed primarily for solar system comets, its architecture could be adapted for interstellar visitors. NASA and several research institutions have proposed similar rapid response concepts. Small modular spacecraft equipped with efficient propulsion could launch within months of discovery. Advances in electric propulsion and onboard autonomy make such missions more realistic than in the past. Even if these spacecraft cannot intercept every object, they can collect valuable data from a safe distance using optical, infrared, and particle sensors. Beyond dedicated missions, existing planetary defense systems may also contribute. Networks that track near-Earth asteroids are being updated to recognize trajectories inconsistent with solar system origins. As detection algorithms improve, these same systems will automatically flag interstellar candidates for further observation. Collaboration is an essential part of this new approach. The speed with which an interstellar comet moves through the solar system leaves little time for a single observatory to gather all necessary data. International coordination ensures that telescopes across different time zones can maintain continuous coverage. Data sharing through open repositories allows researchers to compare measurements and update models quickly. The lessons learned from 3i Atlas already influence how future observations will be prioritized. The comet showed that important chemical and physical changes can happen far from the Sun, meaning that distant monitoring is as valuable as close-range imaging. Observatories are adjusting their schedules to include systematic surveys of the outer solar system, where early signs of interstellar activity might appear. Technological progress also benefits public engagement. High-quality images, real-time tracking maps, and simulation tools make it easier for the public to follow discoveries as they happen. Educational projects now use interstellar comets as examples to explain orbital dynamics, spectroscopy, and the life cycle of matter in the galaxy. This wider visibility helps maintain funding and support for long-term observational programs. Another growing field is laboratory analog research. New facilities can reproduce the extreme conditions of interstellar space: vacuum, low temperature, and radiation exposure for extended periods. Samples of ice and dust analogues are irradiated to observe how molecules evolve. Comparing the laboratory results with telescope spectra validates chemical models and reduces uncertainty in data interpretation. Ultimately, the study of objects like 3i Atlas demonstrates how astronomy, engineering, and data science converge. Detecting and analyzing a transient interstellar visitor requires coordination between multiple disciplines: precise optics, efficient data processing, and accurate physical modeling. Each new discovery acts as both a technical test and a source of scientific information. Over the next decade, the combination of automated surveys, improved sensors, and adaptive mission designs will likely turn rare events into regular observations. As the catalogue of interstellar comets grows, researchers will be able to track trends across dozens or even hundreds of examples. That will transform current speculation into measurable statistics about the composition, dynamics, and frequency of such bodies. The accumulation of data from interstellar comets like 3I Atlas has begun to reshape theories about how planets and smaller bodies form. For a long time, most models were based solely on observations within our solar system. The new evidence from beyond it provides a wider sample set, revealing that the processes of planetary formation are not identical everywhere, but follow the same general physical principles. One of the first implications concerns the diversity of building materials. The mixture of ices, minerals, and organic compounds found in 3I Atlas differs from what is seen in typical solar system comets. This diversity suggests that protoplanetary disks around other stars can vary significantly in composition depending on local temperature, radiation, and pressure. By comparing spectra of interstellar and local comets, researchers can map the range of chemical conditions under which solid bodies form. Another important point involves the timing of volatile retention. The persistence of active ices in 3I Atlas indicates that some comets can preserve volatile compounds for billions of years, even while traveling through interstellar space. This means that thermal insulation in small bodies may be more efficient than previously believed. Understanding how such insulation works can help refine models of both cometary evolution and the survival of prebiotic materials in extreme environments. Theoretical models now include parameters derived from these findings. For instance, the distribution of nickel and iron in 3I Atlas helps constrain the temperature at which metallic condensation occurred in its original disk. Similarly, the abundance of hydrogen cyanide informs models of organic chemistry under low UV radiation conditions. Each of these data points narrows the possible physical range in which similar bodies could form. As these refinements accumulate, they strengthen a unifying idea that the same fundamental physical laws govern the formation of planets and small bodies throughout the galaxy. Gravity, thermodynamics, and radiation act universally, but local conditions create different outcomes. 3I Atlas demonstrates this principle clearly. Familiar processes produce a distinct result when initial conditions change. Astronomers use this information to test simulation codes that model entire protoplanetary disks. By inputting parameters consistent with the comet's composition, they can see whether the model reproduces the observed characteristics. If it does, the simulation gains credibility as a tool for predicting how other disks evolve. If not, the discrepancies point to missing physics or incorrect assumptions about material properties. The influence of such discoveries extends beyond theory. Observational programs are adapting to the idea that interstellar objects are a valuable complement to local data. Instead of focusing only on comets bound to the Sun, surveys now include search strategies designed to identify potential interstellar trajectories early. This shift helps balance the study of familiar solar phenomena with the exploration of external systems. In practical terms, that means adjusting instrument schedules and data pipelines. Wide-field telescopes need continuous calibration to detect faint, fast-moving targets against background stars. Software must be able to distinguish true hyperbolic motion from artifacts caused by image noise or processing errors. International teams coordinate to confirm detections quickly, and assign observation priorities. As these systems improve, the number of discoveries will grow. Each new detection not only provides another data point, but also helps refine the detection methods themselves. Over time, the feedback loop between observation and theory becomes more efficient. Better models guide searches, and better data improve models. The study of interstellar comets also affects how scientists think about the early solar system. If objects like 3I Atlas are common, it is possible that similar bodies once passed through our system during its formative period. Some may even have collided with young planets, contributing material from other stars. This exchange would have influenced the chemical evolution of Earth and its neighbours. Isotopic measurements provide a potential way to test this idea. Ratios of specific isotopes, such as deuterium to hydrogen in water, act as chemical fingerprints that reveal the origin of a sample. If future missions can measure these ratios in interstellar comets directly, scientists could determine whether Earth's water shares a common source with material from other systems. Such comparisons could clarify how much interstellar exchange contributed to our planet's formation. The research also has implications for long-term exploration. Understanding how to detect, track, and analyze interstellar objects lays the groundwork for eventual direct missions to these bodies. Although such missions are technologically challenging, the first steps, precise detection, orbital analysis, and spectral interpretation, are already part of routine practice. Looking ahead, scientists expect that a large enough sample of interstellar comets will allow statistical analysis of planetary system diversity across the galaxy. By examining how often certain elements and molecules appear, they can estimate how similar or different other systems are from ours. This will help answer a key question: whether the solar system represents a typical example of planetary evolution or a rare case. Interdisciplinary collaboration will continue to play a major role. Planetary scientists, chemists, data analysts, and engineers all contribute different expertise to this expanding field. Coordinating their efforts ensures that discoveries are not isolated, but integrated into a broader scientific context. Educational and public programs also adapt to this shift. The presence of real, measurable visitors from other star systems captures public attention and provides a clear way to communicate complex astrophysical concepts. Simple animations of interstellar trajectories or models of comet composition make these topics accessible without reducing their scientific depth. The combined effect of these developments is a steady transformation in how humanity views planetary formation. Instead of a process confined to one system, it is now seen as a repeating event across the galaxy, connected by streams of migrating material. Each interstellar comet observed confirms that the exchange of matter between stars is a natural part of cosmic evolution. The growing knowledge about interstellar comets is gradually changing how scientists think about the structure and continuity of the galaxy. In earlier decades, each star system was viewed as an isolated environment with its own independent history. The detection and analysis of objects such as 3I Atlas demonstrate that this separation is only partial. Matter circulates between systems, linking them through the continuous exchange of solid material. From a physical perspective, this exchange is a natural consequence of gravity and motion. Every star exerts influence over a large volume of space, and the boundaries between these regions are not strict. When small bodies are ejected from their parent systems, they enter trajectories shaped by the galaxy's overall gravitational field. Over long timescales, this field mixes the outputs of millions of stars, creating a shared reservoir of material. Understanding this process allows astronomers to view the galaxy as an integrated system. The atoms in any planet, comet, or star have likely traveled through multiple generations of stellar evolution. A molecule detected in 3I Atlas could have originated in a distant supernova, passed through several clouds of gas and dust, and eventually condensed into a solid body around another star before reaching our solar system. In this context, interstellar comets serve as samples of galactic history. Each one carries a record of its formation environment, temperature, pressure, radiation, and chemical balance, preserved within its structure. By comparing these records across multiple examples, scientists can reconstruct how conditions have varied throughout the Milky Way. This approach complements large-scale astronomical surveys by providing direct physical evidence from individual objects. Another important implication concerns the timeline of material mixing. The galaxy rotates once every few hundred million years, during which stars and their planetary systems drift relative to one another. During each rotation, countless small bodies are exchanged. Over the course of billions of years, this mixing smooths out local differences in composition. The relative uniformity of elemental abundance observed across the galactic disk supports this interpretation. At the same time, the small variations that remain are scientifically valuable. They reveal which regions of the galaxy evolve faster or under different conditions. 3I Atlas, for example, shows lower metallicity compared with local comets, hinting that it may have originated in an older or less enriched region. Such findings contribute to mapping the chemical gradients of the Milky Way. Beyond chemistry, studying interstellar comets also informs the physics of material transport. The way these bodies retain ices and organic compounds over long journeys reveals how stable solid matter can be under prolonged exposure to cosmic radiation. The survival of complex molecules implies that the interstellar environment is not as destructive as once assumed. This insight affects how researchers model the distribution of dust and volatile compounds in the galaxy. From a theoretical standpoint, these results encourage scientists to reconsider how life-related chemistry spreads. While comets themselves do not generate life, they transport its ingredients: water, carbon, nitrogen, and simple organic molecules. The continuous movement of comets between star systems means that the components necessary for life are constantly redistributed on a galactic scale. This idea, once speculative, now has measurable support through direct observation. It does not imply that life travels through space, but it confirms that the materials needed for it do. The same cyanides, alcohols, and hydrocarbons observed in 3I Atlas exist in other comets, meteorites, and molecular clouds. Their presence across different environments suggests that prebiotic chemistry is a universal process wherever conditions allow stability. This broader understanding also influences how scientists define habitability. Instead of focusing only on planets located in specific temperature zones, researchers now consider the availability of chemical precursors as a key factor. The study of interstellar comets contributes to this by showing which compounds are likely to be present when new planetary systems form. If these materials are common, then the initial chemical inventory for potential habitability is widespread. In practical terms, this shift guides future exploration priorities. Missions studying icy bodies, both local and interstellar, are now recognized as essential for understanding the origin of organic material in planetary systems. Instruments designed for such missions focus not only on detecting simple molecules, but also on identifying the isotopic ratios that reveal their origin. The presence of specific isotope combinations can indicate whether a sample formed in a high radiation environment or a cooler, shielded region. As observational data improve, cross-disciplinary collaboration becomes even more important. Chemists, physicists, planetary scientists, and data specialists work together to interpret results. Laboratory experiments validate spectroscopic measurements, and computational models test how molecular structures respond to radiation. This integration ensures that conclusions drawn from distant observations rest on solid physical foundations. In the broader scope of science, the study of interstellar comets encourages a shift from isolated analysis to systemic thinking. It connects astrophysics, chemistry, and planetary science within a single framework, describing the continuous transformation of matter. This systems-based approach reflects a maturing stage of astronomical research, where individual discoveries contribute to a unified picture of galactic evolution. Looking forward, scientists anticipate that the next decade will bring a larger data set and a more comprehensive understanding of how interstellar and solar system materials interact. Each confirmed interstellar comet adds precision to models of galactic structure, just as each new exoplanet refines models of planetary diversity. The combined knowledge will gradually reveal how common systems like ours are within the Milky Way and how interconnected all planetary origins truly are. 3I Atlas remains one of the most informative examples in this field. Its unusual composition, sustained activity, and clearly interstellar orbit make it a benchmark for future discoveries. As more objects of similar type are identified, it will serve as a reference point for comparing data and testing new hypotheses about material exchange in the galaxy. The continuing study of interstellar comets marks a transition in modern astronomy. For most of the 20th century, research focused on describing local phenomena, planets, moons, asteroids, and comets bound to the Sun. Now the field extends outward, connecting our system to the larger galactic context. 3I Atlas is part of that shift. It demonstrates that the solar system is not a closed system, but one node in an active network of material exchange. In scientific terms, this recognition changes how models are structured. Traditional solar system models treated external influences as negligible. Today, researchers include external inputs, interstellar dust, gas, and cometary material, when modeling the long-term evolution of planetary atmospheres and surfaces. Even small contributions accumulated over billions of years can affect chemical balance and isotopic ratios. This new framework influences disciplines beyond planetary science. In astrophysics, it links the local environment to galactic evolution. In astrochemistry, it provides a mechanism for distributing complex molecules between star-forming regions. In astrobiology, it strengthens the idea that the ingredients for life are not confined to specific stars, but circulate throughout the galaxy. Because of this, many observatories now coordinate data in multidisciplinary archives. A single observation of a comet's emission spectrum may appear in chemical databases, dynamic modeling systems, and biological habitability studies. Cross-referencing such data ensures that the same evidence supports multiple lines of inquiry. The case of 3i Atlas also demonstrates the value of early detection and sustained monitoring. Its unusual activity was noticed only because telescopes capable of ultraviolet observations happened to observe it at the right moment. Had those observations not occurred, much of its chemical information would have been missed. This experience has motivated agencies to establish permanent monitoring programs that survey large sections of the sky continuously, ensuring that transient events are documented in real time. Technological development follows the same principle. Instruments once designed for single purposes are now built to be flexible. Detectors can switch between spectral ranges, and software can reconfigure observation modes automatically when a new object is identified. The result is a more adaptive observational infrastructure, capable of responding quickly to unexpected phenomena. The cooperation between institutions has become equally essential. When an interstellar object is discovered, the time window for observation is short, sometimes only weeks. Coordinated efforts allow telescopes around the world to maintain uninterrupted coverage, handing off observations as the Earth rotates. This level of organization represents a new phase in how science operates: global, distributed, and continuous. At the theoretical level, scientists are using data from interstellar comets to refine long-standing questions about the origin of heavy elements. By comparing the relative abundance of metals and volatiles, researchers can estimate how efficiently stars of different ages produce and recycle matter. The patterns observed in objects like 3i Atlas help calibrate these models, providing an independent check on stellar evolution theories. Isotopic studies are expected to play a larger role in the future. Subtle differences in isotope ratios can reveal whether an object formed in a high radiation region, near a young massive star, or in a quiet outer zone of a protoplanetary disk. Because isotopic compositions are preserved even when other characteristics change, they act as long-term markers of origin. Missions capable of analyzing isotopes directly in cometary material could map the diversity of formation environments across the galaxy. The lessons learned from studying interstellar comets extend to mission planning as well. Spacecraft designers now consider the possibility that future missions may encounter unexpected targets. Instruments are being built with broad analytical ranges, so they can collect meaningful data even if the object's composition differs from expectations. This design flexibility increases the scientific value of every mission. Public perception of astronomy has evolved in parallel. The idea that fragments from other star systems can enter our own provides a concrete illustration of galactic connectivity. It turns abstract astronomical distances into something measurable and immediate. Educational programs use these examples to explain gravity, motion, and chemistry in ways that are accessible without oversimplifying. The broader significance lies in how these discoveries influence scientific thinking itself. Astronomy often progresses from the specific to the general, from isolated observations to universal laws. Interstellar comets bridge those scales. Each object offers detailed data, yet together they reveal patterns that extend across the galaxy. This combination of precision and scope exemplifies the direction in which modern science is moving. At the same time, researchers maintain a realistic perspective. Not every interstellar object will yield dramatic findings. Some will resemble ordinary comets, others may be too faint for meaningful analysis. The value lies in accumulation. Over time, the collective data will define the statistical boundaries of what is normal and what is exceptional among interstellar materials. 3i Atlas remains central to this process because it represents a complete dataset: composition, activity, orbit, and long-term observation. It serves as a baseline for comparing future discoveries and testing models of galactic material exchange. Each refinement of those models improves our understanding not only of comets, but also of the processes that shape stars, planets, and the galaxy itself. Looking ahead, researchers anticipate that interstellar studies will integrate seamlessly with other major fields, such as exoplanet research and astrochemistry. Together, these disciplines form a continuous chain of inquiry, from the smallest dust grain to the largest galactic structure. Understanding one part supports understanding the others. The scientific community now recognizes that the boundaries once used to separate subfields are gradually disappearing. Planetary scientists analyze interstellar spectra. Chemists interpret astronomical data. Data scientists develop algorithms that serve both space missions and ground observations. This integration reflects the complexity of the subject matter and the necessity of collaboration across traditional divisions. As new instruments come online, the pace of discovery will increase. But so will the need for careful interpretation. Reliable conclusions depend on accurate calibration, consistent methodology, and transparent data sharing. Institutions are therefore investing not only in hardware, but also in standardized procedures for processing and verifying results. In the end, the study of interstellar comets like 3i Atlas is more than the description of individual objects. It is a demonstration of how scientific understanding grows by connecting isolated findings into a coherent structure, refining assumptions, and updating the collective model of the universe. Each object provides another link in that structure, helping to build a complete evidence-based picture of how matter moves and evolves through the galaxy. The investigation of interstellar comets, such as 3i Atlas, has changed the way scientists define the boundaries of our solar system. It is no longer viewed as an isolated system surrounded by empty space, but as part of a larger environment filled with traveling material. The discovery of such objects has turned a theoretical possibility into an observable assumptions based solely on local experience. The chemical and physical diversity seen in interstellar objects reminds researchers that every system, including our own, is only one variation of a universal process. The legacy of 3i Atlas will likely extend far beyond its brief passage through the inner solar system. Its data are already influencing the design of future instruments and the priorities of upcoming missions. Spectrographs are being calibrated to detect weaker signals. Infrared detectors are being optimized for low-temperature targets. Even mission trajectories are being planned with potential interstellar encounters in mind. These adjustments reflect a growing awareness that the galaxy is more dynamic and interconnected than previously assumed. In theoretical terms, the findings contribute to a unified model of material evolution. The life cycle of matter from stellar nucleosynthesis to dust, from comets to planets, is now seen as continuous. Each phase feeds the next, and interstellar comets are one of the mechanisms that connect these phases across space and time. They show that the building blocks of planets and life move freely between systems, linking individual stars into a broader galactic ecosystem. This concept supports a more integrated vision of cosmic evolution. It suggests that the chemical history of the Milky Way cannot be understood by studying stars alone. The small mobile bodies travelling between them are equally important. By tracing their composition, astronomers can reconstruct the pathways by which elements and molecules circulate. The result is a more complete picture of how the galaxy maintains balance between creation and destruction, formation and dispersion. Such insights have philosophical implications as well. They change how humanity perceives its place in the universe. The material that makes up Earth, the Moon, and every living organism likely includes atoms that once belonged to other star systems. The same process that sent 3I Atlas across interstellar space may have delivered the ingredients of life to our planet. Understanding this connection turns distant cosmic processes into something tangible and relevant to our own existence. From an educational perspective, these discoveries offer a unique opportunity to engage the public with science. Interstellar comets are concrete examples of motion and transformation on a galactic scale. They illustrate that space is not static but filled with activity, a place where matter is constantly recycled and redistributed. Presenting this reality in accessible terms helps bridge the gap between abstract science and direct experience. In research planning, the next steps are already clear. Scientists aim to build a statistical foundation by observing many interstellar comets over the next decades. A larger sample will allow more precise correlations between composition, origin, and trajectory. Missions capable of remote sensing at multiple wavelengths will play a central role, while laboratory studies on Earth will continue to refine models of chemical behavior in extreme conditions. International coordination will remain essential. The detection, tracking, and analysis of transient objects require global cooperation. Data from ground-based observatories, space telescopes, and laboratory experiments must be integrated into shared archives accessible to all researchers. This openness accelerates progress and ensures consistency across different research groups. As these systems mature, the study of interstellar comets will become a standard part of astronomy, not an occasional curiosity. Every detection will contribute incremental knowledge about galactic chemistry, the dynamics of small bodies, and the broader flow of matter. Over time, the combination of these incremental steps will refine humanity's understanding of how galaxies sustain their cycles of matter and energy. The scientific goals align with technological progress. Advances in autonomous spacecraft, electric propulsion, and data processing are gradually making direct exploration of interstellar objects feasible. The ability to send a probe to a newly discovered comet within a few years of detection will mark a significant milestone. Such missions could analyze material firsthand, providing definitive answers about its composition, structure, and origin. In the long term, research on interstellar matter connects with the fundamental question of how unique our planetary system really is. If the chemical and structural patterns found in 3I Atlas are repeated elsewhere, it would imply that the processes leading to planets and potentially habitable environments are common. If they are not, it would highlight the exceptional conditions that shaped our own system. Either outcome deepens understanding of the universe and our place within it. Ultimately, the story of 3I Atlas is a demonstration of scientific method at its best. Observation leading to evidence, evidence leading to new theory, and theory guiding further exploration. Each stage reinforces the next. The comet's passage may be temporary, but the knowledge derived from it endures, expanding the boundaries of what humanity can know and measure. In a few decades, when new generations of telescopes and spacecraft record hundreds of similar objects, the data from 3i Atlas will serve as a reference point, a reminder of the moment when interstellar science evolved from speculation to observation. What once seemed distant and unreachable became measurable and quantifiable, marking another step in the gradual process of turning the unknown into the understood.